In this video, I'm going to demonstrate the code reusing attack. Sometimes when we try to exploit a buffer overflow vulnerability, we don't have a large buffer. What can we do? One approach is that we will try to reuse the available APIs that are already existing in the operating system. Okay, and so again, we are going to try to exploit our variable chat server. And as you can see here, we are given uh, the tutorial in this GitHub repository. And so here we talk about the WeChat server kind of setup and other kind of configurations, but we really don't need such information. And so you can see here, this is our Windows VM. For the demo, I'm just going to disable all the Windows security features. So here you can see I'm going to click this virus and threat protection, then manage settings and this virus threat protect settings. And then I'm going to disable the real-time protections. And so here is if we inject malicious code into Windows computer, the OS may perform the real-time check and may actually kill the process. And you can see we disabled all the security settings in this category. Okay, and so that's fine. And also, I'm going to run our chat server. Okay, and we chat. So you can see I have all the program here. So I'm going to run the WeChat exe here, and so this is our variable chat server. So then let's come back to the tutorial, right? Let's look at this exploit process. And so here we have information collecting, right? And we can use nmap to scan the target computer, in this case, Windows VM. So we will find out the chat server runs at, you know, this IP address, right? Let's look at the IP address of this Windows VM. It is 10.0.2.50. The server runs at the port 9999. Okay, and but anyway, we are going to ignore this step here. And also we can use telnet. So in this case, let me just give you a demo how to use a telnet. And so you can see we can do this. And you can see here it says we can do help, right? And we have so many commands available on the chat server. So here we are going to exploit this GTER command. GTER, nothing, GTER. Okay, so looks this is the right command. If I do this, what happens? Nothing. So here, basically there's space and doing something, then it will give you something back. Okay, so good. So let's see how we can exit this telnet program. So control right square parentheses. Okay. Okay, so then we do quit. Okay. Okay. And so we know a little bit about our valuable chat server. So everything looks okay. And now let's look at how we write the shell code. So that's a key idea here. So basically, as we know, if our target is a networking program, it must have loaded all the necessary dynamic libraries. So now let's see if we want to write a reverse shell code program, and we can actually reuse all the existing APIs already in the target program space. Okay, so in this case, so basically, you can see there are a few things we have to take care, right? A few APIs we want to get information about them. And so on Windows, so WSA startup is going to load all the necessary dynamic libraries. So in our case, our target program must have done this. So let's look at to create, you know, the reverse shell, right? We need the following APIs, the WSA socket A. This will create a socket. And this is the assembly code that is needed to call WSA socket A here. And so basically, you need to prepare all the parameters. Then you call this WSA socket. And so here, let's come to our Caddy VM. And let me see if I have the tutorial or not. No. So basically, I need to come back to here. I need to clone this repository. Okay. Then I come to here. I'm going to git clone this repository. Okay. So I got everything I need. We chat GTER and code reuse. Good. So I want to go to the source code. And here I have all the code. And so I'm going to actually open the code. I need to go to Caddy. Yeah, this is home. This is Caddy, right? And so we need to go to tutorials. Where's tutorial? Okay, here. Okay, and code reuse, source code. So I'm going to use this one. Oh, not this one. Okay, I need to open that, you know, ASM. Okay, so in this case, you can see we need to, this is the socket, right, API. And so you can see here, we prepare all the parameters. Now we need to actually call this API. However, we need to know the address. To make things simple, we are just actually use a program called Arwin to get the API. But in reality, you can actually craft code to do that. So there are existing code online. You can use it. We also have the code, but to make this example simple, you know, we are just going to actually use Arwin to get the, you know, the address of WSA socket. Okay. And so here is what we are going to do, right? So I'm going to open another console here. And so I'm going to Arwin, which is already installed on Windows VM. And this is WS2. I forgot what is the API, dynamic library. And let me have a look. Okay, it should be down here. So WS2 underscore 32. So what is the API? Okay. when by name could find function could error could find function in the library. Let me have a look what's wrong here. WS232. Did I put something wrong here? R1, right? R1 WS2 WinSocket. Did I write something wrong here? Oh, okay, sorry. Okay, and so this is the address, right? And so then we come to here, we replace this address. Good. So they are different, right? You can see it's 771E9B, 1E9B. This is, you can see they are different because on Windows, every time when you restart Windows, those APIs will be put on different addresses. So the corresponding library is put on different addresses. This is ASLR. Again, this is only for the demo purpose, right? And there are ways to find the address by coding. And then we also need to find the address of connect. So in this case, because we are cooking up the reverse shell code, and so we need to know, you know, the attacker's IP, in this case, the caddy VM, right? So our caddy VM has the address of 10.0.2.21. Okay, and so let me come back to here. Okay, so in this case, this one is 22, right? So I need to change this to 21. So this will be 15. Okay, so here is a trick. You can see, you know, basically the IP address will be formatted as an integer. It will contain a null byte. However, in a string, we cannot have a null byte. Okay, and that's why we do a trick here. So you can see this is the integer, right? So I need to change this to one file, so corresponding to 21, right? Other numbers are the same, so 10.0.2.21, right? So this is hexadecimal one file equal to 21 in decimal. So we actually add this number to get another number with no null byte. Okay, so we need to change this to A. And then we need to get the original IP address by doing this subtraction. Okay, so in this way, we can remove the null byte in the IP address. So this is a trick we have to do. And then we also need to know uh, the IP address, no, the address of connect in the memory. Again, we use R1 to do that. Okay, so this is in this one. Okay, so I need to come back. So this 771E, I don't think 77, you can see again they are different. And BC, yeah, BC6980, you can see, yeah, they are different. Okay, good. And so let me double check. Yes. Okay, good. Okay, so then if you know, right, we can use a create process A here to create a new process of a command console, but we are going to actually, assign the standard error, standard output, and the standard input to the socket we have. Okay, and so that's a trick. That's what we are doing here, right? And so in this way, so basically when the collection to the attacker's computer is set, then the command console will receive the input from the remote, server. Okay, so that's what we are going to do. The output will also be redirected to the remote server. And so you can see we did a lot of things here. And so that's all about, you know, start this create process A, uh, creating, the command console process. So again, here we have to find the create process A address in Windows. So in this case, it's in kernel 32 dynamic library. So it's at this address. Okay, and so I need to come back to here. Good. Okay, so this is basically the shell code. And as I mentioned, the shell code will be injected into the target computer, in this case, this chat server right here. And then when the shell code runs, it builds a collection collecting back to attacker's computer. And also, the input handle and output handle and the error handle are bounded to, the socket. So let's come back to the tutorial. And so this is all the process we just discussed. So now we are talking about the exploitation. Okay. And so we just wrote the assembly code of the shell code. So we need actually to assemble it. Right, so here I make sure it's actually saved. So then I come to here, I'm in the red folder, okay? So I can remove the old shellcode .o file. So we don't have that anymore. So then we actually assemble it, get the object code, and the next step is we are going to use a script here to dig the object code out, so which is imaging code. Okay, and so here you can see I need to change this to 7555, the property, right? So that it can run. Extract. So now you can see it can run now. So let's see here, extract. Good. So this is basically the shell code. So let me copy it. Okay. So our exploit code is here. So let me replace the old shellcode with the new shellcode. Okay. And so let's continue to see our exploit. And we have done this step. You can see here. So now, because the shellcode is going to collect back to the cat VM, so we need to start the server, right? And so in this case, we use a netcat to start a server, waiting for the shellcode to connect back. Okay, so pretty good. So here, there's a trick. So I'm going to skip all the steps here to tell you the trick. So this is the stack illustration, right? And so basically, this is our buffer, and so the buffer is owning about this many bytes, 144 bytes, and this is the routine address. Okay, and then about here, then basically we can only use 32 bytes because of this particular GTER command. So because the buffer is very small, that's why we try to use uh, existing code in the memory. That's why we actually try to use the addresses of the connect, right, socket, and create a process. Otherwise, we have to write a lot of code. Okay, and so it's low battery. I have to plug in my microphone power. So now it should be fine. And so let me have a look here. So you can see here. So basically, what what we will do here is you know we need to find out the address of a jump ESP, right? So then when our buffer, right, this Melissa string, overflows the buffer, the address of a jump ESP will overflow, overwrite the return address of a available function in our available chat server. So then basically when the available function returns, jump ESP will run. Then here, the instruction here will run. And this instruction basically does the following thing. It will jump back to the position of our shell code. Okay, and so you can see at the start of this position, we have a NOP slide. Okay, and then so if we actually, you know, run our shell code directly, what will happen? So let me show you what will happen. So let's look at our shell code. So you can see we have a lot of push, but we never tried to adjust, the stack, right? So basically, this shell code is going to use a lot of stack space. So when that happens, When a lot of push happens, what will happen to the stack? Then we have to look at this stack. So basically now, you know, when this shellcode works, before it works, ESP points to this location. So then when this shellcode works, there will be a lot of pushes. So what happens, right? And the stack goes down, it will overwrite our shellcode. So this is not right. So basically the shellcode will overwrite itself because of the use of the stack. So how can we address this issue? And this is the trick we try to find in these steps. So you can go ahead and try to see how it works. Okay, but let me tell you the result. The result is, okay, before the shellcode, we need to add two more instructions. One is push EX, one is pop ESP. So we found out, you know, before the shellcode works, EAX actually contains the start address of the whole buffer. That's here. So basically, you can see these two instructions will do this. It will push EAX, right? Basically, we'll push the address of the buffer onto the stack. Then we do pop ESP. So in this case, right, we actually assign EAX to ESP. ESP contains the address of the buffer. So now ESP will point to this location. So now when the shellcode works and the needed stack space will be allocated down here. So it will not affect our shellcode. So this is a trick we are using. Okay. And so in this way, the shellcode will not overwrite itself. Okay. And so you can read here and understand how we actually, use this Ruby script to find the binary instruction of this assembly instruction. Okay, and also the binary code of this instruction. So that's why you can see here in our final, you know, monitor string, we added these two instructions. Very good. So now let's come back to our attack and code. So let me go through everything here, see if it is right. So here we have Python, right? We're going to use a socket module, struct module, sys module. And you can see here, this export code actually will ask for a parameter, which will be the target IP. Okay, and then here is our custom shell code. And here is our monitor string. So we are exploiting GTER. Just assume this is right. Okay. And then here we have a small, you know, NOP slide. Then here is our push EX, then pop ESP. Then here is our shellcode. And here is a little bit of padding, right? We need the padding to, overflow the buffer so that here the jump ESP address can overwrite the return address of the variable function. So here I regard it actually is right, and this doesn't change because of uh, you know it's from our uh, dynamic library of the chat server, and our chat server and the dynamic library do not use ASLR, so the addresses are fixed. Anyway, it's for demo purpose. And you can see here, right, above jump ESP, then we have this uh, jump instruction, which will jump back to this location. Okay, and then finally we will actually run our attack. So looks like everything is okay. I hope the demo will be fine. Let's have a look, see if it works. Okay, so our server is running. Okay, and then, so let's see here, this Netcat server is running too, waiting for the reverse shell collecting back. So the only thing we need to do here is we are going to perform the attack. Okay, so here is plot 2.py 10.0.15. I hope this will work. Let's see if it works, if we can get the reverse shell. Oh my goodness, it works very well. Okay, you can see we already got into the Windows VM by exploiting the buffer overflow vulnerability in the vulnerable chat server.